everyone. We're now at episode 6 of the WVPodcast. This episode is about math, which is a really cool topic, and we were looking forward to it. We have a special guest and a couple of really awesome students who are talented at math to answer some questions today. All right, and also shout out to John for editing and Jerry for hosting today's stream. Starting with introductions then. See.
I guess I'll start. I'm the least qualified to be on this podcast right now. I'm just a first year student or second year now, that really likes math. I took Math 157 and Math 240 my first year. Really loved them, and I'm currently a math specialist technically, according to Acorn. So, just want to talk about how much I love math.
Congrats on that post.
Okay, cool. Hi. I'm going to my third year. I'm also doing a math specialist. And what else? Oh yeah, my name is Brian. And yeah, that's pretty much it.
I'm Orange. I'm your host. I'm not in math, but I love math.
Hi there. I'm Professor Parker Glynn-Adey. I'm in the teaching stream here, and I did my undergrad in math and philosophy, and then I did my PhD at University of Toronto, where I specialized in geometry. And I really love math. I especially love math that's fun. I love math that's kind of goofy and sort of childish. And maybe we'll talk about that today.
All right, I'm Paul. I like math. Yeah.
Okay, that's everybody. Thank you for those introductions. And getting right into today's podcast. So every episode at the beginning, we have a carryover question from the previous episode, which last week's guests wanted to ask you folks. The question that we have, and last week we had the topic of grad school and the professor that was like Polly. The carryover question for the students is, how do you react when students say, I can't math? And then the carryover question for Parker is, what is it about juggling that gets you so excited, and how is it related to math other than site swap?
Sorry
That
to
was what
interject.
my
Nivi, I can actually share my stream and we can all watch it together.
Oh, right. That's a new thing.
All right.
Yeah, we can directly hear the clip.
Yeah, let's give this a try. Okay, can everyone see that? Has everyone joined the stream here?
Whoa, there it is.
All right, I'm playing this clip in 3, 2, 1. This is the one for Professor Parker.
So Parker and I both juggle quite a bit, and my question to him is, what is it about juggling that gets him so excited, and how is it related to math other than site swap?
Oh, snap. That's actually a really hard question. That's sweet. Should I just hop in on that and talk about that?
Yep.
Yeah, so as I was saying, I like kind of the mathematics of trivial things, childish things. And Professor Polyak asked about this stuff called site swap. And he said I'm not allowed to talk about site swap, though, in my answer. So I'm going to say a little bit about context. So site swap, it's this structure that people discovered inside of juggling. And it was really fascinating because people all over the world discovered it at the same time, roughly in the late 80s. And it revolutionized juggling. Like juggling is 5,000 times bigger than it was and more interesting. And there's all these structures. But Professor Polyak said I can't actually talk about that, which is really hard. So I'm not. So one of the things that I like about juggling is it's something that you can do with your body, and it gets you really physically present. And I think that as math people, we tend to spend a lot of time in our heads, reading books, solving questions and stuff. And it's really a head-focused discipline. And I just like getting out in nature and juggling, and it gives me a way to just like put all that stress, all that like anxiety out, and it's just gone. So yeah, that's kind of my answer to that question. That's the thing that gets me excited, is it's something that I can do that's physical, that's skill-based, and and it makes people smile. I was at the park earlier today, and the little kids are walking along, little 3-year-olds, and they're like, "Oh my gosh, juggling!" They love it. It makes people smile.
Yeah, I remember you juggled on the first day of our Math 232 class, and everybody was just awestruck.
Yeah,
Parker,
right.
Have you had a chance to see Parker juggling yet?
Oh no, I haven't seen him juggle
I haven't
yet.
taken a class with him, so no.
Yeah.
Yeah.
Did you happen to have juggling balls with you?
I might. Just one moment.
This is exciting.
Oh, he's actually going to give a live demonstration.
Comments from the chat. What is site swap? Oh, we probably should ask Parker that. Another comment from the chat. Seems like they all love math. Yes, that's true. That's so fascinating. So Parker's juggling
God.
right now with 3 balls. Wow.
Cool. Yay.
That's super cool.
Yeah. So I guess what do we do now? What happens?
Parker, we have a question from the chat, which is, what is site swap?
Okay. Yeah, I can't resist talking about that. So, to make kind of an analogy with music, site swap is a way of writing down the rhythm of a particular juggling pattern. So site swap records on what beats do balls land. So here I've got 3 objects, and I'm going to just juggle the 3 objects, consistent rhythm. So a ball lands on every beat in this pattern. So this is just written 3, 3, 3, 3, 3, 3, 3, 3. Every beat there's a ball landing. But I can do other things. I can do stuff where things aren't landing every beat. So I don't know if you could hear that, but there's slight pauses there. That pattern's called 4, 2, 3, 4, 2, 3, 4, 2, 3, because there's a beat that's missing. And people hadn't realized that there was this mathematical way of describing these patterns. And people discovered like new juggling patterns that no one had ever juggled before by figuring out what kinds of mathematical structures of beats are possible. So this probably all looks the same on the webcam. I'm sorry.
Looks like the bottom ball never goes up.
Yeah, exactly. So they discovered that one. That one's called 441, and people figured it out like with an equation for the first time. A person named Colin Wright discovered that. So that's a little bit about site swap, but we could talk about that endlessly.
That's really fascinating. Thank you for sharing. Okay, and the question for Akira, Brian, and Paul is, what is your reaction when people say, I can't math?
Neither can I.
Neither can I.
Yeah, I totally agree. I've done so many times -2 equals like 0, and it's like, yeah, that's not what's
Okay,
happening.
like arithmetic math is kind of different from like more proofy math in university, I would say. But
How about you, Brian?
I guess it's true that for some people it takes like less time to understand certain concept, but that does not imply that you cannot understand anything. Like there's nothing wrong with like taking more time. Like I've taken a lot of time, like just like reading over the textbook and then just going over to office hour and everything. So I don't think there's such thing as like I can do math. Yeah. What does everyone else think?
I feel like a lot of it is just overcoming the fear of math that you may have developed in like high school or whatever.
Yeah.
Yeah. I think there's an appropriate kind of like quote from Mr. Miyagi from The Karate Kid, 1984. He says something along the lines of, there is no student that is wrong or bad. It's usually the teacher that has where the fault lies. So I think with math, especially, sometimes it might be the right teaching technique that really gets someone to really engage and get into it. And often people kind of base all of their experience with math on one or two teachers, and that's not entirely fair.
That's so true. Yeah, I completely agree. And we don't have that many experiences with math teachers, in schools. So we have a limited exposure. And coming to university, where I think all of my university math professors have been amazing, that's just a different experience. So maybe students, if they try math in university, I think that's a really cool quote, that it depends on the teacher. Yeah. Okay, so getting into our podcast, part 1 of the podcast is titled Math is Cool. And it's kind of just talking about each of your experiences with math. So the first question that I have for you folks is, why do you like math? What part of math do you find the most interesting, and why? Okay, how about we start with
questions?
Start like order.
I'm gonna have to take a while to think about it. My favorite part of math. Originally, I wasn't gonna do math in university. It was more of just like for a CS post and stuff. I did the math stuff. What was I gonna say? I think it was mostly like Mat 157. I think the professor Yale, she taught it really well. I don't know. It was really nice watching her lectures, but yeah, I would say that played a pretty big part in getting me into math. Just having like nice teachers. What else?
Is there a part of math that you like more than the others?
Well, to be fair, like just one-dimensional real analysis is kind of fun, but because most of it is pretty intuitive, I would say.
I'll go next, I guess. So there's something I learned in like later years of high school when we were doing like competitive math. It's like complex numbers, and then we talked about something called polar form, where you can describe numbers, complex numbers, using like a radius kind of thing and angle. And one thing that we learned was called roots of unity. So it kind of talks about how there are these polynomials and they have these complex roots. Obviously, we learned a lot more about how this is really useful for doing these like really cool summations and stuff like that. But the part that was the coolest for me was seeing that if I were to graph these out, right, these roots of unity, and I were to like use the x, like the real coordinate, as like an x-axis, and I use the imaginary kind of coordinate as a y-axis, and you can put that in Desmos. It's like a really cosine sine kind of equation going on. You notice that they make like a pentagon or like a hexagon. They make like a regular polygon, and I found that was like totally crazy, because like the last time I saw those shapes was like in elementary school. So it was kind of like a big wow moment where I saw like all this crazy symbols just ended up being so.
First time that's happened, just for the Discord server was temporarily unavailable with great timing.
Yeah, things got that awesome.
We can continue. That was very coincidental timing. Yeah, but let's continue. So how about you, Brian? I hope you remember your answer.
Back to that. So I was saying that in first year, I was in a similar situation as Paul. I was just trying to, I guess, like go for comp sci in general. That's what I applied for in the first place. But then, like all the math courses I was taking, was like really interesting. I didn't take math 157 though. I take 137 because, well, I think that's a good level for me at first year. So I did that, and then I guess what I like about math is its abstraction. Like when it comes to like upper year courses, everything is really abstract. But then that gives you the feeling of like you're dealing with something that is like absolute truth, because you can prove it, right? Like math is probably like one of the few subjects where you know that what you're doing is absolutely true. So I just really like that feeling, because me myself, sometimes I kind of I'm hesitant when it comes to stuff in the textbook. I sometimes question, why is it this way? Why is it that way? And I just don't like that feeling. Like, let's say we're talking about some other subject where whatever's written on textbook is whatever it is that we need to learn. And I just don't like that feeling. in general. So math gives me like a way to like, I guess like build on the fundamental blocks of theorems and lemma and whatever, and you can just create your little world based on that. So that's really amazing.
That's amazing. There's definitely like the thought that math is a pure subject because everything can be proven. How about you, Parker? What part of math do you like? And why did you choose it?
No, this speaks to what people have been saying. Really speaks to my experience of it. I like this point about the roots of unity being a really surprising concept that you wind up being perfectly regular, or like one thing that's neat about what Paul said about one-dimensional real analysis is that everything becomes, all the theorems in that course become clearer if you do complex analysis and do things in the complex plane.
Oh yeah.
And this is like, it's this huge story. And the thing that excites me about math is that like, it's this story becomes all the theorems we can all contribute to, and we're just all passing through, right? Like it's been going on for thousands of years and it'll continue for thousands of years. And all the parts like just fit, and it's very exciting. I don't know. I really feel what people were saying there, and the aspect of certainty is so nice. For me, I love teaching math, often because people kind of struggle with it. It is hard. A lot of people say they can't math, and one of the joys of teaching it is to show them that big story, to see that we're a part of it.
Yeah, it's really interesting to see how everything connects. So one person who working in one field might be able to contribute because of some new discoveries. And that kind of leads into our next question, which is, what is your favorite math proof/algorithm? Akira, would you like to answer first?
I kind of already covered, I guess, one with my last answer, but I'll try to find something new. I think I really like the Pythagorean theorem. It's a very simple kind of proof, but I think what's so beautiful and elegant about it is not only how many times you can kind of use it in different ways. It leads to very interesting applications with integrals, right? Where you can use the sine cosine version, and you see that, oh wow, you can do these substitutions, and they're, really really useful in grade 12. But even back in like grade 3 or grade 4, right? You can look at the three sides of a right angle triangle and solve for the unknown, right? It's a very simple theorem with wide-reaching consequences, and I think it's that, along with the fact that it's so easy to prove, right? You could show visual proofs, you can show algebraic proofs. I think that's just, it's beautiful. It's very nice.
I love the water proof where they literally had, like, they filled the triangles with water and then they poured it into the bigger triangle. I think that was really helpful
But
at
you did it
demonstrating.
in primary school or high school? That's so cool.
I think we did it like
Oh yeah, we learned that in primary school.
We didn't.
no, not primary. I think we did it like first year of middle school or last year of elementary or something. I think we did that in like math. But
Oh, that's really cool.
How about you, Paul? What is your favorite algorithm/proof?
What was its name again? I can't name my favorite theorem.
Can you state it though?
What was its name again?
Maybe you
Implicit
state
function
it.
theorem, it's called. Yeah, okay, yeah, implicit function theorem. Because, I don't know, we managed to prove it. So I was taking Math 257 last year. And so the professor, Tyler Holden, he gave us like an outline of what to do for the proof and assigned the whole class, which was like 8 people, into 3 groups. So each of those 3 groups works on part of the proof. And we worked on what we thought was the hardest part, because the other parts we could solve ourselves. And also we want to, boast how we're good at math. But yeah, we couldn't get it for a while. And we were supposed to work on the proof over winter break, and we got it. Yeah, it was a lot of linear algebra, and like it hurts your brain to think about, but like once you get the proof, you feel so satisfied about it. Like you've done something. You know what I'm saying?
Yeah, for sure.
Yeah.
So
It seems really satisfying to
not
prove it
because
yourself.
I like this theorem. It's not because like it's important. Well, it is important, but like not because of its significance in math, but because like I have a kind of personal connection to it. That's why.
Paul, someone in the chat wanted you to repeat the name of that proof.
Implicit function theorem.
Implicit function theorem. Yes,
So
there's your answer.
So just kind of like to summarize what this says, it says if you've got a function that has a graph, and the graph has some amount of slope to it, and you pick some point where it has slope, then near that point there's implicitly an inverse. That function is locally invertible near that
Is there
point.
like a whiteboard
says,
in Discord? I'm not even sure.
Yeah. I don't know.
That's a good explanation.
I could draw it, but it'll take a while.
Yeah, go for it.
I could try drawing it. Wait, let me plug in my.
Yeah. Maybe we
You
can
know
go through.
what I just realized? I don't have my tablet pen.
By the time that we come
I guess
back.
not. We're not drawing it.
Okay. How about you, Parker? What's your favorite math proof?
There's a couple of them. I guess I'll say I really like the Euclidean algorithm. Just to think about that kind of like that big story thing, like Euclidean algorithm, all of our computers are probably doing it right now to make this chat happen. It was developed in ancient Greece in about 500 BC, and it's still the fastest way to get greatest common divisors. It's like one of the fastest algorithms in computer science, and it was developed by a bunch of Greek people 25 centuries ago. And the story continues. The story, like with these unexpected connections, one of the cool things about the Euclidean algorithm is you want to say, okay, what numbers take the longest time to get the GCD? Actually, just before we go on, do people know what I mean by Euclidean algorithm?
Could you please give us?
I do.
Okay, Paul's got it, Brian's got it. But yeah, let's just say what it is. So the Euclidean algorithm, you're given two numbers, and it finds the greatest common divisor of them. So the way it does this is it says, like, let's say we're looking for the greatest common divisor of 2 and 5. It'll say, okay, well, I don't know what that is, but let's reduce to a simpler case. We'll subtract off the 2 from the 5. Now we're looking at 2 and 3. I don't really know what that is. Let's subtract off the 2 from the 3 now. Okay, now I've got 1 and 2. Well, the only thing that divides 1 is 1. Right? That's the only thing we got. So that has to be the GCD. And it proceeds in this very simple-minded way. You just subtract until you have a very simple case to handle. And it's one of these things we always teach it in Math 102, but like it's just so fundamental for cryptography, for number theory. And it opens up all these cool connections. So like in 1888, a mathematician with the last name Lemay, I can't remember his first name, George Lemay, maybe, said which numbers take the longest time to get the GCD? Right? Which numbers require the most subtractions to get down to their simplest case? Does anyone, Paul, do you know this one? Do you know this
I don't.
Okay. Algorithms people, this is like so cool. The Fibonacci numbers take the most number of steps. So
that is so cool.
Right?
Yeah.
Oh yeah, it makes sense.
Yeah.
You
So the
subtract
Fibonacci
numbers, you get the previous one.
Yeah, so like let's say we do 8 and 5. You subtract them, you get 5 and 3. You subtract them, you get 3 and 2. You subtract them, you get 2 and 1. Right? You always get the next Fibonacci numbers below you, and it just goes down like that. So those take the longest time. And that was like the first time in 1888 someone analyzed the runtime of an algorithm. So it's like the Euclidean algorithm is the gift that keeps on giving. It's great.
That's so cool. Thank you for explaining that. I think that was new for most people because even in the chat, people are saying that's cool. Yeah. Okay. Now, how about Brian? Favorite algorithm or proof?
Yeah. So I guess my favorite proof is it's kind of cliche. A lot of people has said this one.
We
before.
lost Orange.
Yeah.
Uh-oh.
Oh,
No,
she's back.
Hello. Welcome back.
Welcome back.
You can continue. She'll
Okay,
reconnect, hopefully.
Cool. So, but it's quite like important to me because this is one of the first proof that I touched that doesn't relate to number at all, I guess. It's actually in graph theory, stated that if G is a connected graph, then G contains an Eulerian circuit if and only if every vertex has an even degree. And this is actually related to the 7 bridges problem. I like this proof because like it shows me that there's like a lot more than just like numbers in math, and I did not realize that until I go into second year when I first like get in touch with like graph theory. So yeah, I think that proof is really interesting to me.
Yeah, I think that ties back to this notion like when people say they're bad at math, they don't know about graphs, right? They don't know that you can do math with just drawing pictures and stuff. So
yeah, exactly.
Absolutely. So thank you for sharing those really cool algorithms and proofs. And if anyone listening has a proof that they think is really cool, put it in the chat and then we can talk about it too. The last question that I have for you guys for this part of the podcast is, what are your thoughts about unprovable statements in math? So the example is like the Goldbach conjecture, which states that all even integers greater than 2 can be written as the sum of 2 primes. I know that Akira had some thoughts about this, so maybe we can start with Akira.
Oh, so I recently took computer science 240 last semester, and I was talking to one of my friends who took the seminar course CSC 199, and we both kind of hit a point where we were talking about axioms and rules and stuff like that and provability, and we both stumbled upon arguably a really important discovery in terms of philosophy and mathematics, which is the Gödel's incompleteness theorem. And that I don't understand the proof fully myself, but the statement basically states that no matter what set of kind of rules or axioms you think up of, there eventually will be some sort of inconsistency, or it'll be incomplete, meaning that you're missing a couple rules here and there. And obviously that's kind of crazy, right? That's basically saying that, you know, no matter what the rule set are, there are some things that cannot be proved. So obviously I don't like that. That doesn't really sit well with me in general. But when it comes to unprovable statements, I guess when I come to the point where I can fully understand Gödel's proof, I'll be able to, I guess, agree with, yes, you know, there are some things that cannot be proved.
Yeah, I just want to add on to that. Like some people might think that, well, what if I just add, I guess, like more rules, more axioms into this like kind of environment? Well, that wouldn't work because there's always going to be something outside of it that has a bigger, I guess, like scope. So it will always be incomplete. If this is true, then it essentially implies that math is never complete. And whatever we're doing right now as mathematicians, it will never reach an end. Like there's no end. And again, I guess it goes back to the point that we're just passengers along this journey. And it's all about the progress. Like I am personally okay with this theorem if it is true. I don't understand the proof either. But yeah, that was just like my opinion on that.
Oh yeah, I'm next. I guess I'm next. Okay, so I'm not sure what you mean by unprovable statements, because you mentioned the Goldbach conjecture. They're unprovable statements, such as like the continuum hypothesis, right? You can assume it is true or not, and you can take it as an axiom or how would I say it? Anyway, it's like, if I remember correctly, it's like someone proved that you can't prove the continuum hypothesis from our axioms. So that's an unprovable statement. Now, the Goldbach conjecture, we don't know if it's unprovable or not. It's more like it's really hard to prove. That's what we think right now. And
yeah, there's this distinction between like unprovable in principle. So yeah, Paul mentioned the example of the continuum hypothesis, and this is a statement that we know, like given the axioms of math, which are usually called ZF, given the Mello-Frankel axioms, you just can't get to the continuum hypothesis. So the continuum hypothesis says any subset of the reals is either finite, countable, or has the same cardinality as the reals. Right? So it's either finite, same size as the naturals, or same size as the whole reals. And there's no other extra sizes in there. And we just, so it was proven in the, I think, 1960s that there's no way to get from ZF to continuum hypothesis. So now people assume that as an axiom. They'll be like, okay, assuming the continuum hypothesis, we can do this extra stuff. But but then like the Goldbach conjecture, we don't know if it's unprovable. It's just like a super hard homework assignment, right? Right. It's this problem that like every number theorist works on, and I think those are really exciting problems to work on. And I think it speaks to the richness of mathematics that there's always going to be stuff that you can't get at from your axioms. There's always going to be new territory to explore.
And we have a question from the chat, I guess relating to the incompleteness, which is, but there are some complete models. If I recall correctly, the model for ordered fields is complete. Is that
right.
True?
Yeah. Yeah. So there's tons of complete models. They're just not of all of math. So this is like a really, this is a big insight that kind of happened in the early 20th century where people got into the process of axiomatizing particular subjects. So like they developed the axioms for group theory. Who in this chat's taken group theory?
Taken or taking?
Taking. Brian's got it. Brian has taken it. But who is currently taking it?
I am taking it right now.
Okay, so we've got two people who've got this then. So they wrote down the axioms for group theory, and those completely describe all of group theory. But there are certain statements that you can't get from those axioms. So for example, a group is like sort of a generalization of the notion of multiplication. But in some groups, you have that xy is equal to yx. In some groups, you have that. And in other groups, you don't have that. So like in the group of real numbers, xy is equal to yx. In the group of matrices, AB doesn't necessarily equal to BA, right? The multiplication just might not work. So from the axioms of group theory, there's no way to get to the statement xy is always equal to yx. You can't start with those axioms and get to the conclusion that you want. So there's this thing where if you have a complete theory, that can prove all statements, you might not, even in a simple case like group theory, you might not be able to get to really simple statements. And in the early 20th century, people thought if you had axioms, you could always prove all the things. Like they were just like really optimistic. They're like, given axioms, we can prove whatever we want. And it turns out that's just not the case, even with simple statements like xy is equal to yx.
But should that discourage anyone? Like what would
did that discourage people? Some people lost faith in math. Like some people were like, oh, this isn't going to solve all our problems, or like there was this kind of this spirit in the 1880s that like if we just figured out logic, if we could just get like the rules of logic and inference, then we'd just be done. Like we could just make a machine that could crank it and it would like do science. And then Gödel was like, no, not going to happen. And some people lost faith, but other people realized that it's also a sign of richness, that there's a lot to explore.
Speaking of which, I kind of recommend this book.
Sure.
How can I recommend a book? Is there any channel I can paste it in?
Well, you could recommend it live, Yeah,
it's Gödel's Proof. You can find it on Amazon. It's like
and who wrote it? Paul Cohen and
Ernest Nagel.
Ernest Nagel. So yeah, Nagel is a philosopher, and he like tried to explain it from a philosopher's point of view. Yeah, Gödel's Proof is super cool.
It's not a really hard read. It's more oriented towards the general public than like hardcore math students. Right? So I mean, if you're interested in this stuff, I'd recommend this book. It's like a 2 to 3 hour read. Yeah.
We have a comment from the chat. Dr. Parker is going to assign everyone the Goldbach conjecture for homework.
Yeah. Sometimes that works. Some really evil professors have done that.
And
sometimes
it
it
posted on
works.
Chegg.
Yeah, just post it on Chegg. Yeah, like some conjectures have been proved by like people coming in at the wrong time to lecture, and they see an open problem, and then they just solve it. Did anyone see the movie A Beautiful Mind?
Yeah.
Yeah.
I like that movie.
Yeah, that happened in A Beautiful Mind. But yeah, are there more questions, more stuff to chat about?
Yep. Okay, so we can move on to part 2 of the podcast then, which is more about math education. The first question that I want to ask is, how does it feel to study topics that are difficult to visualize? Do you have tips for students who need to do this? How about we start with Brian this time?
That's a tough one. I guess by saying hard to visualize, what kind of math is hard to visualize? Can someone else help me out here?
I can kind of talk about on that point. So I took linear algebra like recently, last semester, and so Prof. Hussein was talking about this in one of the channels, and he was saying determinants are really hard to visualize because when you see kind of the whole numbers and matrices in kind of like a very abstract sense, trying to understand what a determinant is doesn't make the whole recursion definition of it doesn't make a lot of sense. It's just like, what does it do? What's its use? Kind of where's it coming from? But he mentioned that 3 Blue 1 Brown has an excellent series on linear algebra, and understanding that, in his words at least, that determinant is just basically the multiplication factor of what the unit square is, kind of the stretch in at least R3, right? And getting that intuition of, okay, we're trying to stretch some sort of unit something, is really helpful for building an intuition on more complicated concepts. Personally, I think that something that was really difficult for me to visualize was recently this summer, I tried taking topology, Math 327. It's a very difficult course. I definitely wasn't prepared as much as I thought I was, but trying to use some kind of visual intuitions of specific cases, like instead of trying to grasp the entire kind of mammoth by yourself, but trying to look at, maybe the tusk or a specific instance of the problem. So I was looking at Mobius strips, which kind of talk about gluing of, topological spaces. That gets you a better idea as to what you're doing, and you can better generalize to a more abstract concept with that specific instance.
Yeah, that's a great answer. And Mobius strips are really interesting. Okay, how about you, Paul?
Personally, I'm not that good at things I can't visualize compared to things I can visualize. Things I can't visualize, I mostly just think of them as just like abstract algebra. So it's mostly just developing your algebra ability based on the rules given. But yeah,
I think that's a good point.
Yeah, so what actually sparked this question was taking Math 232 and how we had to extrapolate to other dimensions. And near the end of the course, it made it interesting to visualize using like level curves, but it still wasn't something that we could picture in our heads, right? So Parker, what do you think about things that are hard to visualize in math?
Yeah. I like that. That's a 232 thing because I really tried to push visualization in that course. Yeah, so there's certain things in math that there's like no. Okay, so there's 2 classes. There's stuff that's hard to visualize and stuff that's impossible to visualize. And stuff that's hard, I totally agree that you need to like practice and build up intuition step by step. Like you can't think of 4D objects on your first day. So there's this kind of like aspect of like practice and like try and make analogies to stuff that you do understand. Like, okay, I want this 4-dimensional cube. But what do I know about 3-dimensional cubes? Or like, I want to talk about 4-dimensional spheres. Well, what properties should they have in common with 3-dimensional ones? So it kind of like builds up step by step. And then for the stuff that's impossible
Is
like one of the things that came up in my dissertation work was I had to think of and I was trying to like work with this object, and I was like, what? Like, it was too crazy. And then I had to do what Paul was saying, where you just retreat to algebra, and you're like, okay, what is this set? What is an element of this set? And you really treat it as like just symbol pushing. And being a good mathematician is having a balance of that, being able to find good analogies to build up your intuition and practice, and then also just being able to like power through hard calculations.
Yeah, I think something like as hyperbolic plane is very hard to visualize. I was recently like watching videos about that, and it just seems so like unreal. I guess that comes down to like we as humans, our perception is limited. Like again, we are 3D creatures, and right now I'm looking at a 2D computer screen, and so anything that goes beyond 3 dimensions is hard for us. And in math, we can like I guess in physics we goes to 4th dimension. That's pretty much it, time. But like in math, we goes like way beyond that because for us it's really abstract. We go to like infinite dimensions sometimes as well. So there are certain things that we cannot visualize. But I don't think that prevent such topic from being real. It's still real. It's just like we couldn't visualize it from our perspective. Yeah.
sometimes I just think, how would math change if we lived in 4 dimensions instead of 3? Like you could visualize complex functions now and stuff. But yeah, too bad we only have 3 dimensions.
Okay, and then I also wanted to ask, so do you guys think there's enough of a balance between mathematical exploration versus graded assignments? So in undergrad courses, so the difference is like between mathematical exploration and graded assignments. Do you think there's enough of a balance? Maybe we can start with Parker this time since he's our prof.
That's tough. Yeah, that's a really tough thing. Okay, so the pessimist in me says, it's very hard to get people to do things that are ungraded. I've really tried to do that, and there's just very few motivations for doing things that aren't graded. So it's hard to strike a balance when people are unwilling to do it. And I think that we should restore this balance. I think that the balance is very, very shifted towards graded assignments. So the whole system set up to essentially create marks. And I think that we should shift more towards this ungraded exploratory thing. Like some of the most rewarding at a spiritual level teaching that I've ever done has just been getting coffee with people, right? There's a grade 9 student that I met because he was doing this visualizing 4-dimensional objects. He wrote some Python code to draw these 4D objects. And his dad was like, I don't know if this is normal. Like,
he's a doctor.
Yeah, so they contacted the math department and said, hey, is there someone who could talk to my kid? And I said, yeah, sure, I'll talk to your kid. And then we just got coffee for a couple of years, and now he's starting at Queen's in September. And there was no grades, there was no assignments, but we just did math together. And that was I think he learned a lot more than if he had been taking high school courses or whatever. But it's very hard to create those kinds of learning opportunities, is my perspective.
Yeah, I would say so too. It's impossible to get like even a majority of people in your class interested in math, especially for like first and second years where they're just focused on CS post and they're just in it to get the marks.
Is Nikki Sigurdsson on this podcast or in the chat anywhere?
She's in this podcast, but I think she might be in the server, or she might be in the past.
At some point, because she created a really cool math club at UTM where they were exploring some open problems. And I went in and I was like, this is the real math. Like, this math club that you have created is super duper cool. And there's just a UTM student who's like, all right, we're going to do some research, and got a room and made it happen. And I think that if you want to do exploration as an undergrad, profs want to do that with you. And also there's students around who want to do that too. And you can explore and like hack and create cool stuff. Like, undergrad is a perfect time for that.
That's amazing. Math clubs isn't something that we've like talked about, but yeah, math clubs, students that are interested in math should join. Okay, another question that I have for you folks is, are there any other topics that you think should have been taught in high school that like maybe everybody should know about but wasn't taught? What do you think? Like, maybe we can start with Akira.
I'm familiar like with the high school education as being kind of we teach about lines in grade 9. Grade 9. Grade 10 we do like quadratics, a bit of trig. Grade 11 then we kind of go more into other functions like sinusoids and stuff like that, and you explore that a little more. But it kind of all builds towards the grade 12 kind of calculus, differentiation, and a lot of that. And I think personally when I took like Math 102 and 157 in first year and 240 and stuff like that, and some of the other courses, I just saw that there was like the door was open. It felt like I was kind of living in this box of, wow, I thought university was going to be Calc 1, Calc 2, Calc 3, all the way until like Calc 14, like it's just calculus all the way through. Like topology, that's Calc 17 or something. But I think I don't know what would definitely be taught in high school that would be super applicable, but it'd be nice if we learned that the world is just not purely building up to calculus.
That's so true. Everything that we learned in high school was building up to calculus. Mm-hmm.
I want to rip out grade 9 and just replace it with Math 102.
Oh yeah.
Just be like, all right, you guys know about numbers? Modular arithmetic, Euclidean algorithm, axioms, logic. I think we could totally do it. I think I'd switch it out for something like Math 102. Another thing I think would be sweet is coding. Coding is so accessible. It's so doable now. And it could totally be part of high school. There's no reason not to. Lots of people are learning to code in high school anyway, and we should just like put it in there. Those are my thoughts.
Absolutely.
I think it's more like I'd rather just rip out calculus and put Math 102 in there. The problem is that I feel like calculus in high school is way too computational, and it's taught in the way that you'll forget it after high school anyway. So even if you get like a transfer credit or something, skipping is a really bad idea. You're still going to have to take first year calculus either way. And still a lot of students struggle with it. So like instead of covering like a lot of topics, and like some schools even go further. My school did some basic differential equations, and frankly I forgot how to do them completely. So less content, more focus on like understanding, I would say, is the way to go.
Yeah, I guess like two things. One is proof, definitely, but not even like hard proof. Just be like methods to do the proof. A straightforward proof, contrapositives, contradictions, whatever. And like I don't think those are just math. It's like way of thinking, right? How do you use your logic to again like argue about something? So that's number one. Number two, I'm a bit hesitant about this. It might be a bit hard for high school students, but I think it's necessary. It's the epsilon delta definition of limits. I think that's the proper way to teach calculus. I don't like the purely computational way of teaching calculus. That's just my personal opinion. Yeah, but I don't know if that one's hard to comprehend for high school.
I heard someone on CBC a little while ago. They're a vocalist or a tenor, and they grew up singing Bach. So they grew up when they were like 6, 7, 8 years old singing Bach. And the CBC interviewer was like, "That's so hard. How did you do this?" And they said, "No one ever told me it was hard. So I just sang it." And I feel that if we just took out grade 9 and replaced it with 102, no one would notice, right? They would just be like, oh yeah, this is fine, whatever. Grade 9's way harder than grade 8 was. But university would seem so much easier. So
Just to go back on Parker's earlier point about math and coding, I totally agree. I think a lot of people that are entering computer science, like I was, really find that they hate math. You know, math is ugly, disgusting symbols. Like, what is that? Who cares, right? But recently, at least in the last bit, I've noticed that there's this beautiful kind of dance that both math and computer science kind of have, and coding in general. Just the ability in coding that you can just start, it's so accessible. You can just open like a tab, find some sort of like a interpreter or whatever for Python, and just start coding immediately, right? There's so many tutorials and stuff out there, and just being able to, test some of these math stuff, just to kind of convince yourself, oh, this is true for sufficiently enough numbers, and this kind of like holds true or whatever. And then even in reverse, I feel like there's just a lot of interplay between the two fields that people just don't really kind of notice and realize, like recursion and induction. Those kind of have a beautiful kind of synonymity between them. Yeah, I was taking a 148, and one of my other classes taught structural induction, right, which is a more generalized form of induction. And all of a sudden, like, all the recursion stuff that never made sense to me, it just bam clicked. It just clicked, and all of a sudden, like, every time I had to make a recursive function, it took like 5 seconds because it was just so clear and obvious. It's just base case, recursive case, right? So yeah, I think
Totally.
definitely leveraging that is super, super cool and important.
yeah, where the high school curriculum is kind of stuck in the 1950s. Lots of the choices that were made so like before the 1950s, high school was different. You proved stuff. It was all you're reading Euclid and like proving stuff about geometry. But then in the 1950s, they're like, oh, we need people who can be engineers because we needed more engineers during the war. And they've just kept it. They've kept it very
Engineering.
yeah. And the high school curriculum doesn't believe that computers exist, basically. And they do, right? We're all on computers right now. All of us have done some amount of coding, perhaps today. And we should teach high school that way.
All right, we're nearing the end of the episode, so I'm just gonna wrap up a little bit. I'd like you guys to come up with a question for next week's folks to answer, just like how we had a question at the beginning of this episode. Again, a bit of a spoiler, next week's episode is about security, like in the context of computers. And we're hoping to get Arnold, like Professor Arnold. Was I muted this whole time?
No, we can hear you.
You're good.
Okay, perfect.
Yeah, we can hear you.
So we're hoping to get Professor Arnold on, so please come up with some questions one question for the professor and the students.
What is your favorite prime number?
Sure. Yeah, actually, that's a good question.
Hey, it's security.
Yep, that is relevant. Okay, and if anyone has questions, just plop them in the chat right now. I'm going to go through the chat and ask the questions.
Sure. I have like one question for Arnold that I'll just kind of pass forward there. So right now we're living in this world where everything is security based, right? We all have thousands of passwords. We all use these digital services online. And I think that the weakest point of the security chain is people who make dumb choices about passwords. So what do you recommend for like good password hygiene and having a good, safe, secure computer system in today's modern internet?
That's such a good question. Okay, it's been written down, and next week we can hear the answer, so please tune in. We have a question from Flofi, which is, how do you strike a balance between the motivational, cool stuff in math and the part that's required for tests? Like that balance between not making your class just be a test prep session and also meeting the objectives of the course on time.
Take courses that you like.
Take courses that you like. Yeah, good advice.
Honestly, I don't see a way that you can do well in a course you don't like. Like, that has been my experience.
Yeah, that's true.
I definitely agree.
Like, I guess the fun stuff that you do are supposed to be identical to the stuff that's on the test, right? That's what the definition of doing something that you're passionate about. If that's not the case, I guess like if you have to take this as a prerequisite of something that you don't really like, I guess time management is really important. Like if you have to do that, yeah.
Also, a good prof makes a really big difference, I think.
I'm gonna step a little bit back on that question. Oh.
No, you're not muted anymore. Your camera is delayed a bit.
Okay, I'm going to step a little bit back on that one and say a lot of courses aren't meant to be super fun, right? They're meant to give you skills. They're meant to like convey some understanding. So when you're an undergrad, you've got this cool opportunity to figure out what you care about, and there's a lot of work to be done. You're taking 5-6 classes. You got tons of deadlines, but I think to make that balance of fun and interesting versus like passing the test, you have to be curious. And like I can remember spending so much time on Wikipedia just being like, what's a groupoid? Or like, what's an exotic seven sphere? And like just like browsing Wikipedia and being like, this is all really weird and I don't know what's going on. So that fun math, you kind of have to bring it yourself. And in university, you've got all these really smart people around and you can go talk to them and like go like knock on profs' offices or go to their Zoom office hours and be like, I saw this crazy thing on Wikipedia and I have no idea what's going on. And that's just a cool way to start conversations. So courses are boring, but if you're curious, you'll find some fun stuff to look at.
Jumping on that immediately, actually, one thing that I spent a lot of time in Prof. Polyuk's office hours, even when he didn't have office hours. I was just in his office. And the thing he had in his office was like a whiteboard, and it had a lot of scary math on it. But it always looked very interesting because I kind of understood like a couple symbols. I was like, oh, I know that. That's a Greek letter, right? Or that's the natural numbers and something like that. And so I guess like working up the courage to ask him stuff like, what's going on that board, and can you explain it to me? And he was amazing, true trooper. He was trying to explain to a poor first year undergrad student who didn't know what he was doing, like what I was doing or whatever. And we got some really interesting conversations. So definitely go to office hours, plug right there. Profs are really fun to talk to.
That is really good advice. Like I've often seen math on professors' whiteboards and wondered what it was. So next time, even if it's online classes, bring a random Wikipedia page, maybe.
Yeah, why not? Right? We're there for you guys, and we want to help. And you're at this really exciting and like tons of time for exploration. So check it out. Are there more questions from the chat?
Looks like that's all. So thank you everybody for joining. Next week's episode, please tune in. And other than that, any closing remarks from everybody?
I just want to thank you all for having me out. This has been a blast. It's great to see everyone again. And yeah, thanks White Van Discord for inviting me.
Yeah, I think I want to take a course with Prof. Parker now. I'm super love the enthusiasm.
Cool. Yes, thank you to everybody else. Have a great week. And that's the end of our podcast. That's a wrap.
Bye.
Thank you. Bye-bye.